Pankaj, our first morning talk will be given by Paolo Villoresi. He is full professor now, and he is the director of Padua Quantum Technology and Engineering. He has published many works in quantum information, optics, etc. So I invite Professor Paolo Villoresi to share this.
Thank you very much. Thank you very much. So, morning, everyone. It's a great pleasure for me to be here. First of all, I would like to thank for the invitation, this remarkable institution, and so, I'm very glad to share with you uh, our research line and the results, looking also at possible collaboration we may have. Uh, Talk today will essentially embrace many things we realized looking forward, developing quantum communication on the ground and in the space in particular. In Italy, but I'm very glad to be here in India. I pay tribute, for instance, for a spectacular, great banyan tree that I've discovered here in Kolkata. And these are the things that say, let you think that, yes, there is a lot to see around the world. You have to go out from your cradle to actually explore. So the title is Quantum Development in the Ground and in Space. Developments means that, well, we have heard, we know about the basic, but essentially we have to keep pushing for going ahead. So the idea is to also show some direction which you shall develop. Okay, so that's the idea. Let's start from where I'm from. Padua University was founded about 800, a bit more than 800 years ago. Okay, out of students that came from Bologna, which is the alma mater, first university in the Western world. Uh, and these students went to Padua to find essentially a different environment where they are free to listen and the professor free to teach. And such a freedom is embedded in the motto of university, freedom for all, whatever, and gonna stay as our say main direction, our North Pole. This has an example into essentially achievements. One was the establishment of the first surgical school with the actual hands-on on the body. That was possible only because of the protection of Venetian Republic that protects against essentially the Pope guard. Okay, and this is the cathedra that Galileo used to teach. And also in that case, physics and philosophy in general was the occasion to be essentially free to discuss and to publish the findings that essentially at the time removed the center of the universe from the earth, okay, and consider science based on observation and scientific methods, okay. Develops as a astronomy, so science, physics, and astronomy school. And one notable scholar is Levi Civita, that provides the calculus that was used in general relativity. A few years ago, we founded a research center of quantum technologies with the idea of going beyond the expertise of a single group. Okay, so this center is essentially the synthesis of scientists from 4 departments: physics, engineering, chemistry, and mathematics. Okay, with the purpose of taking projects that are only say, the synthesis of these activities. So they need to be essentially at least based on two departments, so the people that has to share their knowledge. I have the honor and the pleasure of being the director since the inception. And this is a photo last year for the meeting of last year, where we actually see components from the different departments with different expertise. So, yeah, I would like to provide, to start with some example about the advancements in the quantum communications and some hints on novel techniques that allow it, for instance, some experiments on quantum mechanics in space, okay? And then I would like to provide you a bit of the perspectives of the EU. So just as an introduction, always refer to the concept that quantum communication are based on essentially sharing elementary states. So essentially the elements of the microcosmos that is prepared with the purpose of transmission for implementing a particular protocol, okay? And so this, say, sending is the quantum communication is the most fundamental form of communication because you are sharing fundamental states, okay? And this has both, say, challenges and advantages, okay? The channel through which you are communicating is designed to protect the transmission, but at the same time, it provides the opportunity to probe, sometimes exploit, okay, the transformation of the quantum state, like the relativistic transformation and invariances and things like that. For understanding the role of the channel, we have to go briefly through the concepts that are involved in this scheme, in this say prepare, sending, and measure. Okay, so if we just take the most intuitive example, so the prepare and measure thing. Okay, like for the QKD protocols, quantum key distribution protocols. So the two main steps for this QKD protocol is the quantum communication followed by a classical post-processing, okay? So the sender encode a quantum state taking a classical variable, A, alpha or A, and it encoded in a set of non-orthogonal states. This is, say, a possibility that you only have in quantum physics, okay? These states send over a channel, which can be an optical fiber, free space channel, satellite to ground, whatever. Satellite to satellite, many examples, and underwater maybe. The channel, from the point of view of the QKD, is considered under the control of an eavesdropper that try to steal information, okay? But the linearity of quantum mechanics, and this is a strictly classical feature, forbids the performance of perfect cloning. So if the eavesdropper only can get partial information, okay? But then at the output, the receiver perform quantum measure and obtain a random classical variable beta, okay? And after you have repeated the thing, the post-processing allow essentially to get rid of the shared information with the eavesdrop, which again is something that classically is not possible, and it's essentially the advantage, the edge that quantum information brings into the system. So this is realized, and this is the famous scheme, for instance, of BB84, after Bennett and Brassard, 1984, in which you have these sets of non-orthogonal bases, and you here hypothesize that you have perfect correspondences of the essentially alignment of the bases that Alice and Bob can choose, okay? And the effect of the eavesdropper can be casted in this form. So as we were saying, you may have two mutually unbiased bases, Z and X, okay? You start with the bits maybe we can use this. Okay. Bits that randomly are chosen between 0 and 1, 0 and 1 on both bases, okay, that are encoded in these states. Mathematically, this is the representation. Experimentally, we'll see, but of course, this becomes, say, a selection on a particular state of a degree of freedom of the carrier that you have chosen, usually light. So electromagnetic degree of freedom for radiation at the quantum level. And so you have 0, 1, plus and minus, okay, states, which along the channel are attacked, are measured by Eve. And according to the base that she choose, okay, you may or may not have a transformation that eventually leads to a, say, result that is not correlated with the transmission, and so generate an error. And this error is the valuable parameter that quantum information provides, unlike the classical protocols, for essentially arriving at the end of getting rid of this shared information with the eavesdropper. So now, where the advancements come into the scene. For instance, when you are considering preparing, encoding these states, okay, you're saying, well, 2 mutually unbiased bases, dimension 2, so I have 4 states to prepare. I may use 4 lasers, okay? Okay. If you light each at random, okay, each of these, okay, you will get a sequence of HV plus minus states. You expect that the only difference is the polarization orientation in this case, because for this example, your degree of freedom is the photon polarization, okay? But for instance, these lasers may have, say, slightly different spectral support, say, different spectrum or center wavelength, like, okay? And you may have a possible hacking due to this mismatched spectra. So that's a weakness that an eavesdropper can exploit. And the advancements come when, for instance, you substitute this with a scheme in which you have only one laser. You are modulating the polarization after that. Okay? So this is an example on how say, an initial implementation, straightforward, say, is surpassed. We will get back to this, but just to show the idea. Another, as I underlined briefly before, you expect that Alice and Bob, they share the orientation of the basis, the transmitter and the receiver. They need to be aligned. Okay? Otherwise, you have errors because you have confusion. So here again, you take another schema, okay? That's a standard implementation. You have multiple sources. When you, say, put together the possible eventualities, so horizontal, vertical, and so on, okay, you expect all these, they have to match the orientation, okay? If one terminal rotate with respect to the other, then the vertical is seen no longer vertical, but inclined. And so again, you have Kuber, okay? So this is another possible source of attack. But then there are countermeasures. For instance, if you use another degree of freedom, you combine in the encoding. For instance, you take polarization and you consider the orbital angular momentum, which is the properties of the electromagnetic beam. Yeah, in paraxial approximation, you know, it's a different thing. It's not in full vector treatment, but in paraxial approximation, we have different numbers that describe the state. And you create a subspace in which you combine polarization NOM, okay? You again have the set of 4 states, but these are invariant with the rotation of one terminal with respect to the other, okay? And we, for instance, have demonstrated in free space for the first time the possibilities of doing it. It's a long story, but to make it simple, we essentially create a hypergeometric beam using these Q-plate elements, okay, and we encode the state in a way that essentially this, if found one terminal rotate with respect to the other, essentially the rotation that impact on the polarization essentially is compensated by an opposite rotation on the OM. And so the result is essentially that the Kuber stay low, okay, definitely below the threshold, while if you were using just the polarization, would have seen a rise in the Kuber, okay? So this is a way to contravent this. In this sense, a combination of these 2 degrees of freedom, different, is not exploited for essentially increasing the rate which you are communicating. You may say, I have a larger Hibble space, so I can share more information. You are not exploiting this opportunity, but you are creating this rotation invariant subspace to provide a new feature, okay, this rotational invariance. Another approach is this approach of reference frames independent schemes, okay. There were a number of the ideas and also realization. Our take is that essentially you can realize essentially a schema in which you turn a time beam encoding into a polarization state, but you have essentially to realize the check of the eavesdropper on a meridional plane in the Bloch sphere that you have self-tested initially, and when you essentially have collected this information, then you run the experiments and you check whether you are safe or not by doing these measurements, okay? And this essentially allows to use your system without this perfect matching control. Also, you enjoy having, for instance, a drift in the polarization, which may drift the point of this equator, okay? And so this, in a way, make also the setup easier to realize, less prone to problems. So you see, these are directions in which the things has evolved since the initial statement of the protocols into something that is more agile, more flexible, okay, in a way. So the quantum communication also ventured the space. There are reasons for this, okay? So in this context, we are now in a phase that say have seen initial, say, experimental tests and then demonstration of different realization of protocols as the QKD, for instance, but not only. And now essentially it's a technology to support cybersecurity at the planetary level. At present, strong support on space QKD is pushed by several continents and nations, okay? And the focus is on application. But I'm saying that it's very much needed an effort to keep going the scientific part. And this is, I think, open to the international cooperation, okay? So doing experiments on this. Of course, then the application will come, and that will be, say, nation-centric, and no doubt about it. But maybe still, no, I'm convinced that there still is a moment to look at the scientific thing, and if this country is interested, I think there's a good opportunity. So a brief focus on our activities on this. We started working in opening the quantum communication in space in 2003, okay? When I got a project as a young researcher and the opportunity to work at the Matera Space Center, where they combine WellBI, big antenna looking at the quasars, with satellite laser ranging, okay? This telescope that is 1.5 meter telescope, capable of tracking the satellite on all orbits, okay, that may range the moon, okay. It's a photo of Michus passing on, and essentially where we have essentially turned the capability of this station into a quantum communication hub by essentially realizing sources of quantum state in space at the time there were no active sources available, essentially sending up pulse intense enough that once it hit the satellite and is back reflected thanks to corner cubes on the satellite, well, the pulse that leaves the satellite is actually at the level of, I don't know, a quantum state with a mu of the order of 1 or less, okay? So you have realized essentially a synthetic source of time being or polarized qubits in orbit, and your task is to essentially measure it. Since the initial works in Matera, we developed also other ground stations like this one that is on top of the building in Padova, and we have about 20-kilometer link available to essentially emulate satellite links from a hill in the surrounding of Padova, and many horizontal links at a shorter scale to test the urban conditions. For the purpose of testing the space-to-ground conditions, we've been also carrying experiment for 3 years, the Canary Islands, archipelagos, the famous Tenerife-La Palma link, where you have to fight against a very strong turbulence, okay? In preparation of that, we have many links, horizontal links, and you can see, for instance, the difference. This is a link in the mountain where after 10 kilometers, you still see, can see the ivory pattern. That is, it's not a movie, this, but still has this 0, okay? While if you go to a 20-kilometer link, you start seeing the filamentation of the beam is taken live, so almost collinear, okay? And so you see that on the target, you have this scintillation, which is something that attests to the splitting of the wavefront. And in the Canary link was even worse. Okay, this is a video of the pupil of the 1-meter telescope we've been using, and you see there is a strong scintillation. It was quite worrying at the beginning, and indeed our first scientific result was a random number generator, because this is actually a random number when you essentially put a sort of a chessboard on top of this, and you frame by frame sign where the centroids are present, and this through the lexicography index gives you this. The best we have achieved is to get a spot after this 143 kilometer with the size of the PhD student, okay, which was a human scale facility. On the ground, we have a regional network now working between Padova and Venice with many nodes at the Padova University, and this will be essentially connected, it's going to be connected with the national and the European network for this. And we have one free space link there at the urban scale, one to the hills, free space, and the rest is on fiber. One link is along the highway, so beside the cars there you have the qubits going, okay, and several others, some institution beside the university and regional government, like that. In Europe, in terms of perspective, there are several projects at the national level, Italian Space Agency, at the European level, several initiatives. This is the quantum flagship. It's actually supporting this talk. And several actions like the Marie Skłodowska-Curie program that are accepting PhD students, and very glad to have right now a very bright PhD student from India, okay, working at these topics with us. Okay, we have also a spin-off, Think Quantum, that licensed a few patents from our group and realized them industrially. So briefly going towards how we did it, as I mentioned, we started in space having this synthetic quantum source by sending up a pulse. Looking at the reflection, you see there are satellites that are sort of big cannonballs covered with the corner cubes. Corner cubes are the components you have also on the back of your bicycle that allows the driver to see you, okay, because they are just sending light in the direction of arrival, turning the k vector 100 degree, 180 degree. And at the time, 2003, when I started, there were many things new, and I took the train to Vienna asking the collaboration of Professor Zeilinger that at the time did several experiments ready in the lab, proposing to go with his team beyond the lab to the very long distance. He accepted it, so the first work was done together. Okay, and after 5 years, we reached this peak that attested the possibility to isolate the qubit coming from the satellite. At the time, there was not the possibility to encode information in any degree of freedom, just to the exchange of this single photon. Okay, then we tried now with another grant from the University of Padua, and now just as and the Italian Space Agency, to encode essentially polarization state. Okay, so we have a source at 100 megahertz that was prepared to send up to space with this scheme, and with that we have shown the first Q-Ber measurements, for instance, in space, that at the time was controversial because there were skeptical researchers that essentially consider the ice in the border stratosphere, say, dangerous enough to spoil the polarization state. And we proved it that instead you can do it. So by sending state that belong to these mutually unbiased bases, you see the outcome at a different and correct port time by time, and with a rate of over 100 click per second, we have shown that the Q-Ber may be as low as 1%. Yeah, for different satellites. And if you are using satellites that are not preserving the polarization state, this is a very simple feature that is provided by the metallic coating on the back of the corner cube. You have the Q-Ber that is almost, it's about 50%, as it should. Of course, you need to demonstrate it single photo level, okay, by using the radar equation that is well known in the satellite laser ranging business, okay, and this was the case, and indeed this was actually the first demonstration in space. It was the highlight of the Physical Society of America in 2015. We were very proud that it was together with the discovery of the gravitational waves. Then the Chinese launched MICHUS, and this was the actual first fully fledged demonstration of quantum sources in space that, yeah, I think you're aware, performed not only the quantum key distribution, but also entanglement distribution, teleportation from Ali in Tibet, and connected with the ground network, creating a very big network. Okay, there is now the successor of MICHUS, Jinan 1. Okay, last week the corresponding paper appeared in Nature, and they have improved a lot the pointing capability, so that the beam now is suited to be received by a very compact receiver on the ground, so no more the meter-class telescope, but much small one. It was indeed a huge, say, endeavor. They exploited this source we will return. Okay, this is the Hyponiac source, And this is an image of the satellite, which is sort of a small satellite, and much smaller is the terminal on the ground, which is very encouraging for the applications. Okay. These, say, protocols, of course, constitute a big quantum leap in the essentially in the scientific scene, because it essentially cleared the role of quantum information thanks to the violation of Bell inequalities, and have shown many protocols that realize it. And for these three gentlemen got the Nobel Prize 2022. And Anton mentioned it explicitly, the satellite quantum communication in this talk. Beside polarization, of course, light has also a degree of freedom. One, the temporal modes, okay? And I was mentioning before, you may exploit this considering the possibility, the opportunity that they may provide, okay? So we tackle this degree of freedom for a test that will be a different thing, so testing the superposition principle. And for this, we have a scheme in which we prepare a state that has two temporal lobes, okay, that is simply obtained by using our scheme at 100 megahertz that produce pulses that are sent to an unbalanced Mach Zehnder, okay. So you have a short and a long path, and you send over to the satellite and back, okay. In the essentially space part, it acquires a phase between the two lobes of the wave function, okay? It is phi of t, okay? So not a fixed phase, a time varying phase. And the state is then analyzed back using the same interferometer. And so what happened is that from one port, you may detect events that corresponds, these are showing in time, to the first one is the one in which the photon has chosen the short path to get out, and short path to get out and short path to return, and so it appears, say, early in time. The other one, the opposite one, is the one in which you have long path to get out and long path to come back, and it appears the latest. And these are unique processes; they don't interfere. While in between, just in the middle, you have the event in which you have chosen. You can describe the result with the superposition of the process in which a photon has chosen the short path to get out and the long to come back, plus the one in which has chosen the long path to get out and the short to come back. And these two eventualities comes at the same time, but they are different, so they interfere, okay? Which means that essentially the satellite that is moving, okay, it's always moving with respect to the ground station, it's approaching, then going away, okay? Essentially is seen at different position when it reflects the first or the second part of the wave function, okay? How much? Well, you know, in LEO orbits, satellites are running like hell, 7 kilometers per second, okay? And the unbalance is 3 nanoseconds, about 1 meter. Say, who cares? 3 nanoseconds. But 3 nanoseconds times 7 kilometers per second makes a few microns. Who cares about a few microns? So you care about a few microns because we are actually looking at the phase of something that has a wavelength of alpha micron. Okay? So if you count for this motion of the satellite that is always changing in time, okay, you can see that you have a modulation of this phase between the two lobes of the wave function that essentially during a passage, so it's simply because when it's approaching in the satellite word line, when it's approaching, you have essentially that this comes a bit closer with respect to the preparation, and when it's going away, it's happened the opposite. And the radial velocity is always changing, and so this phase. Okay? So if you look at the distance in green, okay, this is the actual approaching and going away of the satellite, and the phase in radian goes from about -400 to 400 pi. They change a lot already with 1 meter of imbalance. And then if you compute the probability of having a constructive or destructive interference at the output, okay, you see that this probability jumps very rapidly from 0 to 1, okay, and essentially this is regulated by, okay, the visibility, which in our case is almost 1, and this phase, which is these things covered by this writing that is proportional to beta, the Einstein beta, so V, the relative velocity divided by C. And so it can be seen as a, say, instantaneous also velocity probe. And we have folded in phase reconstructed the orbit, and you clearly can see when you have constructive or destructive interference, okay, that you compare with the histogram, particularly focusing at the central lobe, in which you not discriminate the phase. So this is just the sum of the other two lobes, and you see a clearly difference with this, and you can see the visibility of this. So testing essentially the validity of the superposition of this state even after a path more than 5,000 kilometers. Okay. This idea was taken very say recently by the Chinese group, Jiang Weipan always, in 2024, when they considered this experimentally in order to essentially enhance the visibility, the precision, and indeed they did it simulating a path in 8-kilometer link in Shanghai. Okay, we have seen this degree of freedom as an opportunity. Okay, we will say, okay, with respect to polarization, it shows much more the transformation in the channel. So maybe it's say it's cumbersome to handle with it. So it's chosen for one of the is a mission. Okay, but at the same time, it's an opportunity because it's revealing a lot the transformation that are ongoing. And so in the context of, say, probing quantum mechanics and curved space-time, okay, considering deploying a long baseline, essentially we were thinking of casting the famous Colello-Verhausen-Werner, the cow test, okay, that was done with massive particle with photons, okay. And so we had a series of a paper together with Danny Turner, a theorist that is working in Australia at the moment, that was also put in this recent review on the quantum experiment, fundamental physics experiment in longer baseline quantum optics, together with NASA. And essentially the idea is to exploit this temporal superposition, okay, on a very long link, and by essentially accurately removing the Doppler part, you may have access to the subsequent term, which is essentially related to the gravitational change between the ground station and the satellite, and particularly when you have inclined and elliptic orbit like the Molniya orbit, this is quite evident. Okay, so it can be cast also as a test of the Einstein equivalence principle when you see actually a shift in the frequency that is essentially a consequences of the conservation of energy, and can be considered like this. Okay, so well, you then need to be able to discriminate very well the paths that are coming back. Okay. And this is an example on the status of the art. The timing resolution over space link is vital. Okay, it is on ground, but even more in space, because photons are coming from the heavens at all times, okay, at all frequencies, and you have to sort out your own qubits among the sea of noise. So, of course, when you consider the application, the protocol, things like that, the signal, the generated correlation due to photons, as the final secret key for ISQIC references, scale with the number of uses of channel per second. Okay, but these high rates are both wishes and feared. They are wishes because they increase the performances. Okay, at the same time, they ask for better and better discrimination of Alice state at the receiver. And also, from the satellite point of view, cranking up the generation rate also requires more energy, okay, which something that the energy the satellite has to take care. Values went from 100 megahertz to 625. That is the actual value of GNAM1 to be okay. To actually demonstrate at the single photon level the capacity of probing the return, we've done a series of experiments based on just the return at the single photon level. We obtained using satellite in MEO, 7,000 kilometer, the result of about a quarter of a nanosecond, okay, resolution, with just this, and instead by combining the qubit thread with essentially intense pulse interleaved in time, okay, so using two sources with essentially this performance, 100 kilohertz at 10 picosecond, 200 microjoule. It is an industrial laser, by the way. We were able to go down to about 35 picoseconds, okay, of the Gaussian part, okay, which say gives you residuals of the order of a fraction, small fraction of the millimeter in the ranging. So these numbers are encouraging for cranking up the speed. At the same time, we developed a technique in which synchronization can be relied only on the qubit stream using some patterns. This is currently employed in our demonstration on the ground. We call it qubit for sync, and looking forward also the application space. About the fundamental tests, we've spoken of polarization and temporal beam, but at the same time, there is also the possibility of combining them to look at some fundamental ideas, okay? And another attractive, say, challenge is to address the delay choice, okay? Gedanken experiment put forward by John Wheeler. This is based on the debate among the giants in the 30s on the possibility of revealing at the same time both the wave-like and the particle-like properties of a quantum object, okay? And Bohr stated that actually you can choose at any time, even very late, which type of measurements you have to perform. And this indeed was the base of this Gedanken experiment of Wheeler that essentially is synthesized by saying that you can prepare states and over to a measuring device like an interferometer, but this interferometer operates only if it's complete. So if the final element, the final beam splitter is inserted, okay? So if you have this inside, then you can see essentially an outcome that is related to the different phases. You again the two arms, so it's actually a phase meter, okay? If the element is removed, then you have access essentially to another information that is particle-like. So essentially it tells you whether the photons has traveled, say, the lower or the top path. Okay. So according to the present or not of the elements, you have a particle-like or a wave-like type of measurements. Okay. So he proposed to do this by essentially doing the delay choice, so choosing at the very last time this. And so we did in space. So we were combining on the same photon, the same flying photon, the choice that was assigned to the polarization degree of freedom and the phase assigned to the temporal degree of freedom, like I've just shown. Okay? And essentially, we've been using the same similar scheme in which now you have polarization that is swept or not according to a quantum random number generator we've been using, and it's synchronized with the launch. So essentially, if you have that the essentially duration of the two alternatives are matched, so you are picking only essentially superposition of the two paths, then you have the wave-like analysis, you have the interference, you have this peak that goes up and down, okay? While if you separate the two paths, so if you essentially go the short way and going out and the short way getting back, or the long way going out and the long way coming back always, then you have two separate peaks in time attesting one path or the other path. So this is the particle-like, and this is the wave-like behavior. And by choosing the type of measurement randomly with a quantum random number generator, when the photon was already in the way back, okay, so after entering the system, essentially being reflected from the satellite, then you encompass this, say, Gedanken experiment, and essentially the satellite waterline is this. You choose in the future of this event the type of measurements, and at the end we have seen interference or which path, so the particle-like, that can be interpreted as this. So if you look at the contrast of the particle-like, you see that you have about 95 visibility of essentially same result, leaving only 5% to the wave nature. While if you look at the interference, you have more than 40% of visibility. So this is clearly incompatible with the objective interpretation, for which you can have a particle or a wave, but not essentially a quantum object in which they are both essentially synthesized by the quantum state, and the wave or particle nature is revealed according to the type of measurement you are doing at the end. Okay. And so this was demonstrated in the quantum span according to Wheeler. The Wheeler idea. Okay, this idea of choosing the right path was indeed attractive, because there was also another approach, experimental approach to another problem, so another loophole that affects quantum measurement. For instance, if you go to belt state analysis and you're using temporal modes, the three lobes that I described before are essentially a possible cause for a loophole, because it's been demonstrated that you may have essentially the correlation that comes from the classical theory, so the existence of hidden variables that can be essentially at the end, if you post-select the measurement only looking at the interfering path, the presence of the hidden variable cannot be excluded because you are throwing away these side lobes. But if you devise a way in which you don't have the side lobes, so you organize an active switching in front of the interferometer that are testing the state, and this active switching is essentially sending the short path to the long path in the measurement and vice versa, then you only get the interfering part. And so the result are then loophole free for this post-selection thing. This scheme was realized in bulk in the experiment in 2017, and has been then integrated thanks to a European project a few years later, and appear on a paper that integrated, thanks to these friends and collaborators, the person that devised this loophole, together with Alan Cabello, and with groups with in Linkoping also, we being able to address these things and demonstrate with the integrated realization, the violation of Bell inequalities with the essentially no side lobes. Essentially, we cancel out these two lobes. The temporal modes then are indeed intriguing. Okay, there is a need of having very clean, very say pure state, especially when you are dealing with high loss channels. And for this, I would like to briefly introduce one of the advancements on the generation of these states. If you consider the properties of a Sagnac loop, well, it's stable because essentially in the interferometer, Sagnac interferometer, essentially you have the two alternatives, two arms actually going the same path. So a deformation in the path affects both. And so it's much more stable with respect to, for instance, a Mach-Zehnder interferometer. So if you have the task of generating temporal modes, okay, you can consider having a pulse that is split into two and generate a clockwise and counterclockwise pulses, okay? And if you have a nested interferometer here, then you create essentially early or late pulse that you can make to exit. If you do nothing, it goes back from the port, okay, with which I get in, okay. If you instead change the phase, you may select to have the early or late or the superposition of the two to get out from this other port of the initial beam splitter. And so essentially this way enjoy the intrinsic stability of the Sagnac and allow, say, the fast switching among the desired states. You have essentially to induce these phases using, in principle, three phase modulator, okay, here. And you may also synthesize the scheme by essentially only using one modulator, much cheaper, okay, and choosing the moment in which to act according to the passage of the clockwise, so it comes earlier, or the counterclockwise, early or late, okay, so different moment in time that allows you at the end to essentially realize the same as if there were three modulators. And moreover, if you change the amplitude of the modulation, you also can get the decoy state that are needed in some protocols, okay? And putting these at test, we have seen that the intrinsic stability and the cancellation that you have of the non-idealities in the beam splitter speaks very well about these schemes in the sense that when you generate, for instance, early and late, the Kuber, that is essentially the presence of the other state, the unwanted state, are found to be record low. We are talking of 1.6, 1.4, 10 to the minus 5. So this is the actual record of Kuber, low Kuber. And in the realization, you see that you can actually go with a very low Kuber at source in the realistic demonstration. You can also use the for qubits if you say split the imbalance into more paths. Okay, you can then modulate accordingly. And this is the scheme if you have multi-ports, so one in and out, but you can, sorry, this one, okay, one in and out, but you can also realize it with the standard beam splitter, one in, two out, okay, into configuration. So for temporal modes, you have good schemes, but this is a Sagnac, and again, this is another example of the evolution, can be exploited also in the polarization codec. Polarization is good in space, as I mentioned already before, for the stability, okay? You have essentially a simple receiver, no perturbation due to atmospheric propagation, okay? Of course, satellite moves, but with respect to the temporal modes, the rotation is very minor. It's about 60 degrees, so a radian along the entire passage. And you can see it, this green curve is Michus that you can see corresponds to, well, a rotation that was actually less than a radian in a passage over Matera, okay, our telescope. And for this, we're considering doing the polarization encoding in a stable way for space. And this is the idea of the Hyponiac schema, in which, again, you have the clockwise and counterclockwise propagation, unbalanced modulation. So you have the modulator in an asymmetric position, so you can essentially decide when to act, when the clockwise part pass through or when the counterclockwise pass through. So you have early and late modulation, okay? And again, if you do nothing, you have the pulse back. If you act, then you can generate the polarization state that are needed in the meridian of Bloch sphere, okay? So essentially, you have the photon that is split into two, and according to the moment in which this is acting, you can generate the needed state. These also have shown very low Q-bar, okay, of the order of part of thousands. This has been also combined with the intensity modulator to do the decoy state and polarization encoding as needed. Okay, this was say awarded, is patented, and also you recognize this scheme that is on board of Jinan 1, and very much like yesterday, Professor Kumar, also as say, I can see that our idea was brought to space by the Chinese with success. They did an excellent job. Also in their case, they have almost 30 dB of contrast, and they say describe this that is citing our publication as the advancement in the encoding of polarization qubits. Very briefly, I'm doing 5 minutes. Good, yes. You need random numbers, and these are indeed valuable elements for not only quantum cryptography, but for many applications, say modeling, classical cryptography, post-quantum cryptography in particular, gaming, many other things. Okay. We have a research line since 10 years about on this idea of exploiting the Heisenberg uncertainty principle for pushing essentially a measurement at the fundamental limit, okay, in which you actually are probing something that quantum mechanics can prevents to be clearly determined, okay, and so these things using suitable POVM, essentially you do both the scheme in DV, in discrete variable, as well as in the continuous variable, and you are in both cases probing the fundamental limit with essentially an outcome that in the particular case of the continuous variable is actually the result of the fact that you are trying to essentially probing the quantum vacuum, okay? This is an exceptional source because it's very broadband. So we have demonstrated that if you integrate this with an heterodyne measurements, so you are measuring at the same time QMP, okay, you may go with a source that runs at over 20 gigabit per second, okay, and that is suitable for space as well. As I mentioned, the combination of this random number generator and QKD say schemes with the different encoder that I've shown you has been brought around. For instance, this is an example of the Vienna link of hybrid, say, free space and fiber link, even with rains during the path, that is not affecting as much as one think the propagation, especially if you are running in C-band, okay? And this allows also to reduce the number of terminals, because you don't need to have, if you're using polarization encoding, the bob at the feet of the terminals of the telescope, but you can distribute the signal in town, in this case Vienna, and reduce the number of boxes. We've been addressing also application in railways, energy distribution, many other things. An example is the securing of the control signal that characterize the GPS type, the Galileo version of it. You may need quantum memories for channels. We've been venturing into the free space realization of them together with the group of Dan Figueroa in Stony Brook, okay, when it was possible to cooperate. And we ended up with this demonstration of the essentially home deep done with the two quantum memories separately. This scheme, again, example of improvements. This is a scheme of killing the two side lobes and getting only one is, for instance, one of the achievement of Kannan, our esteemed PhD student from India. These are the boxes that been realized by the spin-off that say working worldwide on both ground link, free space link, and stuff like that. So in these more than 20 years, we've been developing these techniques in space. This is a timeline. Unfortunately, this suffered a lot from the pandemic and the consequences of the pandemic. The access of the observatory there was, say, not encouraged, to say the least, and also change in mentality later. But we are pushing hard because there are a lot of experiments to be done, okay, and we are eager to work at that. In Europe, there is a big initiatives, the flagship on quantum technologies. In particular, the Quantum Communication Network for Secure Communication is called QSNP, okay, Quantum Secure Network Partnership, okay, and it has essentially several directions to work with. One is devoted to improving the QKD protocols, the way in which you essentially may envisage the security proof, the agility, intermodality, and implementation. This is WP2, which I'm the WP leader, and it is a very active and exciting cooperation because there are more than 40 groups and they are experts on many things to work together, covering essentially all Europe, and started in 2023, and we are working on this. I think I don't have time to cover the interstellar communication thing, so let's go, and I would like to go to the conclusion. So Space Quantum Com established with a variety of protocols that match things on the ground. The demonstration been done, big investment is on the way, but my message is that beside this, there is the need of going forward with the experiments, and these are things that can be done internationally. And the vision is, thanks again to QSMP partnership to support me, that Space QCOM has no limit but just horizons. So the higher you go, more you can see reach. Thank you for your attention.
Nice talk. What really is going on in this experimental situation? He nicely expressed. Now, there are questions.
One of your slides, you showed that you have received signal from 20,000 kilometers.
Yes.
So, you like which kind of telescope you have used there? 1.5 meter or
Yes.
50 centimeters?
Yes.
So you are going for new already.
Yes.
From.
That was essentially the reaction because I was discussing with the European Commission on the usability on the NSS satellites, and at the time we have only the result. But beside the AGSI, the first experiment that exchanged with the satellite at 1,600 kilometer, we extended it to 7,000. Okay, with the satellite of the Laser Engine constellation. And we say, wow, but you did 7,000 while these other are 20,000. Okay. So we went back to the telescope. The experiments are now, you see.
Very interesting talk and it triggered several thoughts. So I'll say about the foundational part that you mentioned, wave particle duality and other things. What I thought was one of the things is temporal correlations between the two paths. That is through Leggett-Garg inequalities, not the kind of Bell test. So has that occurred to you to check the temporal correlations? That is one question. And the other one in the foundational side again is the closed time curve kind of approach. Closed time curve, that is one travels and comes back kind of a thing. Approach has been used in with entangled states in metrology, and similar approach with time superposition is another random thought that occurred to me while listening to. So I just wanted to ask you.
Thank you. Very interesting questions. Well, about the first, yeah, the Leggett-Garg are indeed intriguing inequalities, and if you look at the experimental approach that has been used, for instance, by the highly respected group of Professor Sinha, the POVM is based on this possibility of blocking one of the beam during the process. Okay, and so far we hadn't found a way in which this can happen in the space channel. Okay, because you are leveraging on this passive reflection there. So yes, it's interesting, but it takes an active things that we don't have yet. Okay, there. And on temporal loop, yes, that is something extremely exciting in the sense that well, our take follows an idea of David Deutsch, then developed by Tim Rolfe, and as you may know, he ends to essentially a bound on the visibility of entanglement that essentially was within the domain of Michus, and they did the experiment and found visibility higher than that bound. And it was a science paper a few years ago already, 2019. And then Tim Rolfe changed the bound, okay? And so we have a much tighter, say, corner in the parameter space to look for that. That is essentially connected with the existence of wormholes. And we had a debate in the European Space Agency, and we invited the team and actually asked, but where have to be this wormhole in the universe? It has to be close to a satellite or not? Because if it's close, maybe you can send a satellite in the wormhole. But no, there was not a clear answer to that. Maybe you have. No. We would like to send a satellite into the wormhole. Okay.
So you used free space method for satellites, right? But satellites may be vulnerable to cosmic effects, and and also they are a moving they are a moving body. I have read that moving bodies do affect entanglement in some manner. That entanglement may be it can be affected adversely. So, have you considered this effect?
Yeah, this is one of the proposal in the review that I've mentioned with NASA. Okay, so at the moment we don't have the tools to actually point at some, say, bound in the result. For instance, Michus did not work on that because he couldn't in terms of resolution. It is something which, well, we are working, but you needed to do a few intermediate steps, okay, that already have raised the bar to jump over quite a lot, and we are not there yet. And this is the reason why I was mentioning the need also having young brains so to work on this. Okay?
And also one that is there a blue and red shift effects observed in the polarization? Do they
Yeah,
affect
the effect
polarization?
is minor with respect to the one you have on temporal modes. Okay, there are papers on the calculation on this, yes, but it's very, very hard to see. Already the red in the temporal modes are it's about 5 order of magnitude weaker than the Doppler curve. Okay, so you need to say be able to attest the Doppler to better than 5 order in order to reveal the other. This is our task. I mean, this is also the idea of the PRL of John Way last year, but you still need, say, to go beyond on the experimental side on that, okay, to address the temporal thing. The polarization, it's hard, because to get to that precision, you need at the end a lot of energy, okay, that tells you the output. Means that you have the need of collecting many photons, okay, and from space. They are coming back, but not that much.
Okay. Sir, my question is that what is the role of orbital angular momentum in communication?
Role, yeah, it's an opportunity. So it's one has a degree of freedom that you may choose to adopt. I've shown you the advantages of combining it with polarization on ground links because you were able at the end to measure the entire thing. For satellites, well, we thought about it, but I've tried the Canary Islands, and due to the diffraction, the OM essentially they have a bound that it increase in the divergence that it increase with L. Okay, we have a paper on that, and so the larger the spectrum you're using, the more you have the enlargement of the beam. And in order to essentially retrieve the signal and have good contrast, you need to gather it all. Okay? And so at some point, well, you do the math, and your telescope is in the need of being larger and larger. And in addition to that, since you are essentially sending over, well, if it's in space, it's fine, okay? So in the vacuum, it's fine. But if it's in air, that is usually around when you are around the Earth, well, you are probing different patches of atmosphere that due to turbulence is different diffraction order. So you have a significant demonstration, the formation of it, that essentially mix it up the L. So as I said, I've tried the Canary already in 10 kilometers. There was spoiling. It was devastating. Okay?
As we are as so
Yeah, I wanted to follow up a little bit on your this experiment where you have temporal modes getting reflected from the satellite. So I can understand that you have a small time difference between the two pulses and satellite is moving, so that causes some change, the reflection from one to the other. But you also mentioned something about the effect of the gravity itself. So is the assumption that the gravity is changing over that few nanosecond times?
No, not that. The effect of the redshift is seen when essentially you are considering an altitude of the ground station, an altitude of the satellite, different ones, and then you have essentially that the frequency is redshifted when you move from satellite to ground, and this is only seen in the one-way path. So in our case, we couldn't observe it because essentially we were generating the photon, sending to space, and then back, whatever the distance is done both ways. Okay, and so if you calculate the effect is really minor. You still have a triangle due to the motion of the satellite, but it's really minor. Okay, while
Okay, I think I get
yeah, the 5 order of magnitude, which is already say, a very minor effect, when you are going satellite to ground or back.
So I request all other participants and etc. to talk to in the tea time. Okay. So we thank the speaker again for his.
Thank you.
So we will submit start at 11:30. So go ahead.
Yeah, those who are having poster presentations, please assist our volunteers to arrange the posters. Thank you.
Hello. Hello.
Hello, hello.
Yes, sir. You are audible. Can you?
Very good.
Hello.
Yes, yes, yes.
Yes, yes.
You can
You
hear
are
me.
audible. And can you please change the slide? I just want to check it is okay.
Yes, let's do. Um,
Yes,
like
yes. Fine. It's fine. It's fine. Okay. We'll just start in 5 minutes. So.
okay, okay, good.
So, Julio, welcome.
Hello, thank you.
Hello, thank you. Mhm.
Thank you.
So, our next speaker is Julio Chirivella. He is very famous in quantum information foundation, and he's doing a lot in this area, and he's now at Hong Kong University. So, I request Julio to present his talk today. Okay. Thank you.
Thank you. Thank you very much for the introduction. And thanks to the organizers for the invitation to this nice conference. I'm very sorry that I cannot be there with you. Unfortunately, I had the teaching and department meetings between yesterday and today, so I couldn't travel to Kolkata. Anyway, I hope I will give you an enjoyable talk on a pretty foundational topics. This is not even the foundations of quantum mechanics. In a sense, is more about classical physics. So the talk I'm going to present is about quantum foundations indirectly. What I want to do is to challenge some of the usual oppositions that we have between classical physics and quantum physics, and especially the opposition that we normally have between the idea that classical physics is a deterministic theory in contrast with quantum theory that is fundamentally indeterministic. As you know, we are in the International Year of Quantum Science and Technology, so I think it's a good time also to look into these foundational questions and try to understand better what we say about quantum theory, also by contrast with our theories, with other theories. And a typical thing that we used to do is to contrast the quantum theory with classical theory. So with the composition of what is classical mechanics, Newton mechanics, and classical probability theory together. So when I say classical theory, I mean both of the things together. When we think of classical theory, we normally regard it as the gold standard of a theory that reflects our intuition. So usually we say that classical theory is intuitive, whereas quantum physics is counterintuitive. So why is classical physics intuitive? Because normally we think that this classical physics, the classical theory, describes a world that is made of objects, and all these objects have well-defined properties, and these properties are independent of whether we measure our systems or not. So this is like the famous anecdote about Einstein saying that the moon is there even though we don't look at it is kind of expressing this general intuition, this general feeling that we think of classical physics as describing objects that are there, no matter whether we look or not, and that have properties, no matter whether we look at these properties or not. But now I would like to be a bit of a devil's advocate here and ask, well, is this gap that we intuitively feel between classical and quantum physics, is it really such a large gap as it seems at first sight? So this is, so let's try to look into details on what is especially the gap in the common understanding of classical and quantum physics. So in the common folklore, we think that the key difference between quantum and classical physics has to do with the role of probabilities. So if you look at the basic textbook interpretation of quantum theory, you find it statements like quantum theory is a fundamentally probabilistic theory. It only predicts the probabilities of some measurement outcomes. It doesn't tell us which outcomes we are going to see. Whereas if you think of the typical interpretation of classical theory, this is a fundamentally deterministic theory. When we put probabilities in classical physics, these probabilities only reflect our personal ignorance. When there is an agent who doesn't know what is the position or the velocity of a particle, this agent would assign a probability distribution, but there is nothing fundamental to that. In reality, we always think that classical systems have well-defined properties. Now, in quantum physics, we think that the probability of an outcome, the probability of an outcome will quantify the likelihood that we will see that outcome if we do the corresponding measurement. Whereas in classical physics, again, we don't need to think about measurements. We think that the probability that a particle has a certain velocity or a certain position is the probability that a quantity, that a physical quantity has one value independently of whether we measure it or not. So that's the kind of the canonical opposition between textbook interpretation of quantum theory and the textbook interpretation of classical theory. Now, recently, there have been a few works that somehow challenged this opposition between these two different interpretations of probability. And one of these has been proposed by Gizen and Del Santo. So what they made was to propose a variant of classical theory, so a modified classical theory, where the values of the classical quantities are not fully determined. So maybe you can specify the first 10 bits of the position or the velocity of a particle, but the remaining bits remain undetermined, fundamentally undetermined. So this variant that they proposed as a toy theory, basically. So this variant of classical theory has several features that are pretty similar to features of quantum theory. And in fact, they went a step further. They even argued that this variant of quantum theory, where quantities are not fully determined, would actually make sense physically in a world where we can only store a finite amount of information about different properties in nature. So in a sense, this is mostly a toy theory, but it could also have some physical motivation. However, the way that this works is that it requires to change some classical probability theory and to change the interpretation of probabilities there. So one could always take the same theory that Gizen and Del Santo proposed and just change the interpretation and say, well, I still want to think that there is an underlying value, and I just take your probabilities as the probability that the true value has this particular set of digits. So this is an alternative, a variant of classical theory and an alternative interpretation of probabilities. What I would like to do today in this talk, what we have done in our work, is to go a step further, to do something slightly more radical. So what we do, and what I will show to you, is another toy theory. is another toy theory that includes classical theory as a special case. In a sense, we have a subset of the systems, of the physical systems described by our toy theory that would be the classical systems. And within this theory, this bigger theory, we have a way to falsify the assumption that classical systems, classical values are predefined. So in a sense, we can imagine an alternative world described by this toy theory, where in principle one could falsify the traditional interpretation of classical physics. So what does it mean? So technically, I will show you a toy theory. If you look at this fancy picture I put on the left, this is a picture made with AI, where I asked the AI to draw an island. So this island that you see here is the island of classical physics. Is a place where whatever experiment you would do would obey the laws of classical physics, in particular of classical probability theory. If you do a measurement, there are no complementary observables, there is no entanglement on this island, everything follows the normal rules of classical theory. So the people who live on this island would make experiments and could still be convinced, well, they would see that these experiments are described by classical theory, and they could still be convinced that classical systems, the systems on which they do their experiments, have a well-defined property prior to the measurements that they do. However, our toy theory describes a bigger world than the world of this island. So there are more systems that are available in the world of this toy theory. And an agent who has access to this bigger set of systems can falsify the statement that the systems in the classical island have predefined values for all of the possible properties. So an agent from the outside in this toy theory can falsify the traditional interpretation of classical physics within the island of classical physics. So that's kind of the rough program of the talk. And now I will kind of go into a bit of the details, of course, and say what do I mean by these general statements. So this toy theory that I'm presenting is contained in a joint work with Lorenzo Giannelli and Carlo Maria Scandolo. Lorenzo is a PhD student here in Hong Kong, and Carlo Maria Scandolo is a professor at the University of Calgary. So all that I'm going to say and much more can be found in this paper that is referenced here. Okay, so first of all, what do we mean by a theory? I mean, in different areas of science, people mean different things when they say a theory. For example, in high energy physics, people say theory to mean a Lagrangian, for example. Now, what I mean here is something pretty specific. Basically, the work that I present is in the area of general probabilistic theories, and we apply a specific framework in the area of general probabilistic theory that is called the framework of operational probabilistic theories, OPTs. So roughly, what an OPT does is to describe a set of physical systems that is closed under composition. So let's say quantum theory would be an OPT. You have the qubits, the qubits, and then you can consider composite systems of qubits and qubits and so on. So whenever you have two systems A and B that are described by the theory, also the composite system AB is described by the theory. Also, there are states, operations that you can do on all these systems and on all these composite systems, and all the operations that you can do can be described by circuits in the same way as we have quantum circuits in quantum information. Now, for every system, the theory would specify what are the possible states of the systems and what are the possible processes that that system can undergo. For example, in quantum theory, the states would be the density matrices, and the processes would be described by unitary operators, or more generally, by completely positive trace-preserving maps. So that's what we have is the kind of a general version of this. And of course, the theory will specify which experiments we can perform, and the theory will make predictions about the probabilities of the outcomes of these experiments. So like in quantum theory, we would have the analog of the Born rule, a rule for predicting the outcome of the experiments. So long story short, an OPT is just a framework that allows you to talk about all the things that you would talk about in quantum theory, just without assuming quantum theory and without assuming the Hilbert space framework. So the specific toy theory that I discussed today is a toy theory that is made with the two basic types of systems, so the bits and the anti-bits. So the bits are the bits as you know them, as the word says. So these are two-dimensional classical systems with the two perfectly distinguishable pure states, 0 and 1. And in general, the mixed states are mixtures of 0 and 1. The possible physical processes on a bit are just, well, the reversible processes are just bit flips. And the non-reversible processes would be described by conditional probability distributions that the bit makes a transition. There will be another system that we call the anti-bit that locally looks exactly the same as a bit. So again, an anti-bit would have two perfectly distinguishable states, 0 and 1, and mixed states that are probability distributions. Now, the difference between the bit and the anti-bit has to do with the way they compose. So when you put together two bits, the composition is classical, so you get the same thing that you would get normally in classical theory, so you just get two bits, 0, 0, 0, 1, 1, 0, 1, 1. And the same when you take the anti-bits separately, two anti-bits together would compose classically. But when you put together a bit and an anti-bit, you would have some more complex type of composition that is not classical anymore. So the difference between bit and anti-bit appears when you put them together. So they compose in a strange new way. So in a sense, you can think of the anti-bit as a sort of anti-particle of the bit, some particle that has the same state space, but can be distinguished by some other property that is not described by the theory. Okay, so basically our toy theory describes a world made of these two types of systems. Now the bits here are these red balls, and the anti-bits would be the blue balls. So if you look at only at systems made of bits, everything would look classical. All the processes that you see, all the experiments that you can do, all the states that you can observe are classical states. So everything is described by a completely classical probability theory and completely classical dynamical laws, if you put the dynamical laws there. The same if you look only at the anti-bits. So a world made only of anti-bit would also look completely classical. However, we allow these bits and anti-bits to be correlated in strange ways, so that if you look at a bit and an anti-bit together, you can discover some non-classical phenomena. So these phenomena appear when you have hybrid systems made both of bits and anti-bits. So the simplest case where you see something non-classical is when you take a bit and an anti-bit together. The way we construct the composite of a bit and anti-bit is to use the Hilbert space framework, because we are used to it. We are kind of working in quantum information. We are used to do things with density matrices. So we use the Hilbert space framework, however, without assuming that quantum theory describes the world of our toy theory. We just use it as a mathematical toolbox. So with this toolbox, we can define the pure state of a composite system of bits and anti-bits. So the pure state would be of two types, either the even type or the odd type. You can see here with the cat notation. So a pure state of the even type would be a coherent superposition of cat0 tensor cat0 and cat1 tensor cat1. So the bit is in the state 0, the anti-bit is in the state 0, or the bit is in the state 1, the anti-bit is in the state 1, and here we have coherent superpositions. The other type of pure states would be of the odd type, where you have cat0, cat1 on one side, there cat1, cat0 on the other side. These are all the pure states that we allow, so we don't allow superpositions of the type cat0, cat0, or cat1, cat0, so the parity must be fixed. We can think of this as a two-qubit system with a super selection rule on the parity. We ask that the parity is fixed. The mixed states are just the mixture of the density matrices corresponding to these pure states. So we can think this really as a theory, or as a kind of subset of quantum theory. The measurements, again, here are described by resolutions of the identity in the same way as you would do in quantum theory, except that we have this super selection rule on the parity. So what are the local measurements if you look at this state space of a bit and an anti-bit? An ideal local measurement on the bit, the one that distinguishes the values of the bit, is just this projective measurement, ket0 bra0 tensor identity or ket1 bra1 tensor identity. And the same for the anti-bit. We would have a measurement of the value of the anti-bit done by these projectors. All the other measurements that you have locally are a noisy version of these ones, where you kind of randomize the outcomes that we get. Now, when we measure a bit and an anti-bit, when we measure only the anti-bit from a pair, what we do is that we collapse the bit into a mixture of pure states, and the pure states can only be ket0 and ket1. So we never see superpositions when we when we annihilate the anti-bit by measuring it. When we destroy the anti-bit by performing a destructive measurement, the bit can only remain in a mixture of classical states, as it should be. The thing is that in this composition, the only product states are the classical ones. So either the bit and the anti-bit have value 0, 0, or they have 0, 1, 1, 0, 1, 1. Every other state would be an entangled state and would not have a definite value of the bit and the anti-bit separately. So in this case, our toy theory has entanglement in the sense said by Schrödinger. So here we can have maximal knowledge of the whole without maximal knowledge of the parts. However, if you look only at a bit and an anti-bit composite, this is different from the composition of two qubits. For example, with local measurement, you cannot really detect this entanglement. From the point of view of local measurements of the bit and the anti-bit separately, this state would look the same as a mixture. So this theory, in the language of quantum foundation, our theory is non-locally tomographic. It doesn't have the property that local measurements identify the global state of two systems together. And also, if you look at only local measurements done on a bit and an anti-bit, this theory doesn't allow you to violate any Bell inequality. So it's kind of a mild type of entanglement. Now, of course, the toy theory is not defined only for one bit and then one anti-bit. In our paper, we define the general composition rules for every system made of some number of bits and some number of anti-bits. I will omit this because it's a bit complicated, but the moral of the story is that we are able to put together a theory that is consistent. In particular, it satisfies the property that if we take a composite state of two systems together, let's say an entangled state of system A and system B, whatever A and B are, if you measure one of the two systems, you collapse the other system to a valid state. So everything is self-consistent when you do measurements. Now, the interesting thing with this theory that we cook up is that we can find a violation of Bell inequalities pretty much in the same way as we have in quantum theory. In particular, well, I showed you that you cannot have a violation of Bell inequalities just with one bit and with one anti-bit. But now, what if Alice and Bob have two copies of a state? So Alice has one bit that is entangled with one anti-bit in Bob's laboratory, and Alice also has one anti-bit which is entangled with one bit in Bob's laboratory. So this can be two copies of the same state, just swapping the bit and then the anti-bit among the two laboratories. So when they do this, it turns out that they can violate Bell inequalities, so they can test the correlations between the measurements that they can do on these two sets of systems, and they can violate Bell inequalities. In particular, we find that they can violate the CHSH inequality by the maximum amount that you have in quantum theory, so by 2 square root of 2. And the way we violate this inequality has a special feature, that one of the settings that Alice will measure in order to violate the inequality corresponds to just measuring the value of her bit. So let's say if Alice gets the input 0, the measurement that she has to do is just a measurement on her bit. She can ignore her anti-bit and just measure the bit. The outcome of that measurement would be one of the outcomes that appeared in the CHSH correlation. Now, the interpretation of this, of the fact that we have a violation of the CHSH inequality, is that the value of that outcome, in particular the value of the bit that Alice has in her laboratory, cannot be predetermined. I mean, the assumption that that value is predetermined can in principle be falsified by doing an experiment that witnesses this violation of the CHSH inequality. Now is a good moment to ask how much time do I have to finish now? I understand that we should be probably close to the
Around
end.
5 minutes.
5 minutes. Okay, I will spend these 5 minutes giving a bit of a technical insight in how you would falsify the idea that Alice's bit has a definite value in a word described by our toy theory, and I will leave the conclusion out. I will not discuss the conclusions. I will just leave this for discussions later for the question part. So, how do you violate the assumption that the value of Alice's bit is predetermined? Well, what would it mean that value is predetermined? It would mean that there is an on-tick model or a hidden variable model, in other words, where the hidden variable is some lambda or some on-tick state. This lambda has a probability distribution, and the measurements that Alice and Bob do produce outcomes A and B for settings X and Y that follow some response function, some conditional probability distribution. Now, locality here would be the statement that the minimum locality condition is that this response function is no signaling from Alice to Bob. So for every value of the hidden variable lambda, the setting of Alice cannot signal to the outcome of Bob and vice versa. So this is kind of the minimum locality condition that we can ask. And the condition that Alice's bit is predetermined. So Alice's bit corresponds to the outcome when the setting is x equal to 0. So this would correspond to the situation where the marginal probability distribution of the outcome for x equal to 0 is picked around one value. So there is one value A star, that is the outcome that is predetermined, and the probability of that outcome is close to 1, is 1 minus epsilon for some epsilon larger than 0. So this is the condition that Alice's outcome was predetermined. And now what one can show is that every model that satisfies this condition, so every model that satisfies locality and has a predetermined outcome for Alice's bit, would have a CHSH violation bounded by this quantity, by 2 times 1 plus 2 epsilon. So if you pick a small epsilon, there will be a bound here. And the fact that we can violate the CHSH inequality up to the maximum value 2 root 2 shows that in principle, in the toy theory, we can violate this bound. So we can falsify the hypothesis that the value of Alice's bit was predetermined even up to some small epsilon. This is all I wanted to say. So long story short, we have this toy theory that includes classical theory as the theory describing a part of the world. And in a word described by our toy theory, it is possible to falsify the assumption that classical systems have well-defined properties even before the measurement. So that's all for my talk, and I'm happy to discuss more in the question period.
So, for nice talk, thanks, the speaker. Now, question? Hi, Giulio.
Hello.
Oh, okay. Hi, Giulio. So, the Bell theorem basically says that you cannot have theories which are local and counterfactual definite. It seems that your theory is both non-local and non-counterfactual, right? So, I mean, usually, is that right?
I'm not sure. Can you elaborate more on how would you read this?
So usually, the interpretations of quantum mechanics are either non-local, like Bohmian theory, or non-counterfactual definite, like Copenhagen quantum mechanics. And I'm not aware of anybody who has done an interpretation of quantum mechanics that is both non-local and non-counterfactual.
Well, what we do here is just
yours, of course, is not an interpretation of quantum mechanics.
Yeah, exactly. I was about to say this. So we just provide a toy theory, and the interpretation is like a game that you can play on top of this toy theory. See, how do we interpret this? in a sense, is a quantum-like theory. So we can try to do all the interpretations that we normally do in quantum theory and just apply it here.
Yeah, my question in another way to put it would be, could you create an interpretation of quantum mechanics that is both non-local and non-counterfactual definite, starting from your toy theory?
This I don't know. This I don't know. But what I know, for example, is that in this theory you could have a many-word interpretation where you really think that what would be this measurement is just a splitting of words, even at the classical level. So even the classical probability would be a splitting of word in this theory. So this can be done. But the main point of the theory was to say that you could have a part of the word that is described completely by classical theory. So people who do experiments there would see always outcomes that are consistent with the classical description. And yet, from the outside, one could falsify the assumption that their systems have predefined values, have predefined properties, in the same way as we do in quantum theory.
Okay, great. Thank you.
Thanks.
Thanks, Julio, for nice talk. This is Manik. Yeah.
Hi, Manik.
So you said in your theory, this maximum Bell violation is 2√2. It's coming.
Yes.
So is there any way, means something to some assumption in your theory, means there is the symmetry condition is there to relax it to get the Bell inequality violation up to 4 means peer correlation kind of things.
Mm.
So why I'm asking this question, because if the symmetry condition in some means we can relax and get up to 4. On the other hand, from the information causality or different principle, we know, okay, correlation cannot have Bell value more than 2√2. Then this principle and this symmetry, there might be some connection or something. Is it possible something?
One could try to do something similar to what we have done by incorporating PR box type of correlations. We haven't done it. So I cannot comment more on this. The reason why the maximum value is 2√2 in our theory is that from the way we construct the theory, the state spaces that we have are always subsets of the state spaces of quantum theory. So we build this basically from quantum theory by removing some of the states and making everything consistent. So since all the states and all the measurements are a subset of the quantum states and measurement, we cannot have violations that are bigger than the ones in quantum theory. So one could ask if this is because our theory also satisfies properties like information causality. This we haven't looked in. So this I don't know. And on the other hand, another open question is the one that you asked. So can one produce another toy theory that contains classical theory as the theory describing a part of the world and also allows for PR box correlations of the classical systems with some other systems that is far away or some anti-classical systems. This could be done possibly. But again, we haven't done it, so I cannot say too much about it.
Right. Thank you. Thank you.
Thanks.
Thank you for the interesting talk. I just wondered that if you have a 3-bit kind of a system where you have a 1 bit, 1 anti-bit and 2 bits, like 3-party system with combining your bits and anti-bits within your classical ontic model, let us say. So there are in quantum theory you have things like the whole is determined by the part. That is 3-party state can be determined by its 2-party and other things. So I thought if it cannot be done in your classical theory, because classical probabilities do not have a unique assignment with the help of its marginal probabilities. But in quantum theory, we do have such possibilities into your bit anti-bit theory would be interesting, is what I thought.
Yes, so you're thinking of a sort of a version of the marginal problem here in this theory. Yes, one could think about that. Actually, it's nice that you mentioned this tripartite system because actually these type of systems are the main headache, the main technical difficulty in building a consistent theories. I mean, thinking of the basic bipartite systems, one bit and one anti-bit, was very easy. So we had it already in an earlier paper almost 10 years ago. But then we realized that defining a consistent theory with arbitrary numbers of bits and arbitrary numbers of anti-bits has more constraints, because we should be able to define these composites independently of which systems we compose first. Do I take one bit and an anti-bit first and consider the composite states and then the ones with one more bit, or do I do first 2 bits and then I combine the composite of 2 bits with an anti-bit? So these problems of multipartite systems were actually the main technical challenge in building a consistent theory. And eventually we found a solution that is consistent. Maybe it's not the most elegant solution, maybe one can still do better, but we managed to have a consistent notion of composition for all the possible composite systems in the theory. Once we have this, we can do two things, as you suggested. One is to look into problems like the marginal problem, see how the kind of the entanglement in this toy theory works. On the other, again, is to change the toy theory and to try to find the new composition rules that are more elegant than the one we have for multipartite systems. I mean, it's not written in stone that one could use the same rule that we have. One could try to cook up a new toy theory that has a similar feature. The interesting thing that I find also is that when you combine a bit and an anti-bit together, basically you get 2 qubits in a direct sum. So in a sense, one can think of a qubit as the result of, one could split the qubit into two parts, one being a bit and another being an anti-bit, which kind of resonates with some ideas that we have when we do things like teleportation or dense coding, that we always send 2 bits for transferring a qubit. So it seemed to have some interesting connection with that. But again, this is mostly at the superficial level. We still haven't discovered any particularly deep connection on this front.
So thanks, the speaker again. Okay. So
Thank you.
Okay, for his nice talk. Okay.
Thank you. Bye-bye.
Bye. Okay, our next speaker is Professor Usha Devi. He is doing quantum information and foundation for a long time. I personally know him for a long time. So I invite Professor Usha Devi to use it.
Slide. This one, right? That's fine. Thanks, Devashish, for your kind words. And I am here between lunch break and my talk is in between, sandwich. So anyway, so let me, what happened? Okay. All right. So I thank the organizers, Pankaj, for inviting me here. I always find it as an opportunity to come to Kolkata, land of its own culture and its beauty in its own. So I made it a point to come here. So thanks. I just want to give my talk on heat exchange fluctuations, that is heat distribution, but my talk would give kind of a bird's eye view on thermodynamics, fluctuation theorems, and especially Dzarzhinsky-Osik heat exchange fluctuation theorem. And our approach comes with Wigner function. That is how Wigner function will bring a change in the Dzarzhinsky-Osik theory. So this is, and when we did it, it entered into a lot of different kind of discussions we entered in. So I just want to say thermodynamics as a bird's eye view. I like this statement in the review. If physical theories were people, thermodynamics would be a village witch. So that's what was said in a review article. And then Einstein says the only theory with universal content, which I am convinced that within the framework of applicability of its basic concepts will never be overthrown, which we have been seeing even within our quantum thermodynamics. And this is something just I found it very interesting when French people started thermodynamics. It was, say, dates back to 1452 to 1515, where all processes for perpetual motion should be abandoned by French Academy. But then England took over, and English people could put a patent on steam engine, and England became superpower than France because they could make use of heat in these things, etc. And then the first law, most other people have joined there, and then the second law, where you would say heat goes from high to low temperature, and the story goes on. And finally, the energy of the universe is a constant. Entropy of the universe approaches its maximum is what we stand now today. So now I just, we know that in equilibrium thermodynamics, we have the theory formulates some kind of universally valid statements based on our phenomenological observation. And if we want to go out of equilibrium, we have to reformulate them. Where does that come from? So the stochastic fluctuations in our out of equilibrium, this would impact the laws of thermodynamics, is what is known. So how do we come to terms with it? So what are we interested in basically as random variables basically are work, heat, and entropy. Suppose I take what is work done and heat and entropy as variables, and their stochastic averaging is what we obtain. In such a sense, we have we can define in classical theory, we have basically a trajectory, and on the trajectory I can define what is heat as a variable, work as a variable, etc. But when it comes to quantum theory, we don't have such phase-space trajectories. Different trajectory approaches are there, but what is the phase-space trajectories here? Has it been investigated is the question. So this Dzarzhinsky and Ozick kind of Dzarzhinsky-Crookes relations, they take two-time projective measurements, which I will outline. So basically speaking, what I want to again talk to you is a bird's eye view of thermodynamics. So there are new precision experimental techniques which we have, and testing the limits set by thermodynamic theory is being done, and there are the Maxwell-Demon has been kind of demonstrated on an electronic chip. So when you try to have a Maxwell-Demon kind of a experiment, you do find that the demon also gets heated up if one doesn't know. So that's the kind of experiments which are done. And I just want to, we know the definitions basically in quantum theory. What is our internal energy? It is an average energy. And heat is basically rho dot h of t. Rho changes and trace of rho dot h is average heat, and average work done is rho of t h dot. If h is static, then you don't have a work. And change in internal energy is essentially a combination of the two basically that gives you what is our first law of thermodynamics. Fine. And free energy is F is U minus Ts. This kind of into quantum theoretic world. And now comes to what are fluctuation relations. So these describe the non-equilibrium transformation of a thermodynamic system, and this constitutes basically a refinement of the second law, which I will just mention as I go on. So these connect basically the probabilities for quantities like work, heat, entropy to their counterparts on the time reversed setup. I have a forward time trajectory, and then I look at what is heat, work, and entropy. And if I come back, that is, if there is a time reversal symmetry, I would expect the same, but it doesn't happen. The probabilities would be suppressed in the reverse direction. These are what are seen by non-equilibrium thermodynamics. So these are derived based on thermodynamic properties of microscopic systems, fine. So now, if I take the heat exchange fluctuation, we want to use Wigner function approach for this, and we choose an appropriate system for that. So first come back to what is the exchange fluctuation theorems. This has been done in the case of work in 1997. That is probability of the entropy in one direction or work done in one direction, work in the other direction. Actually exponential of that this quantity has been seen. That is a old story, fine. That is ratios of the probabilities in the forward direction and backward direction. There is a ratio is not simply 1, but it is asymmetric. That has been noticed earlier. And now, if at all I come to the main content when I have no work done, but only the heat exchange possible. So in such a case, what happens? So this is Dzarzhinsky-Ozick paper in 2004, and what they show is probability of heat in the forward direction to probability of heat in the reverse direction is exponentially suppressed, which I will try to say, where delta beta is the difference like this. So this, what is happening? Okay, let us now look at what is Clausius's inequality. So if I take heat flow into system A, that is QA, and if I have, if TA is less than TB, that is A is a colder system, B is a hotter system. So if at all I have put it here, Q is positive. So that is the way one can understand the second law of thermodynamics. Heat flows from hot to cold system. And then Dzarzhinsky-Ozick relation, it talks about strict directionality of thermodynamic heat flow and its time. So that is, if I say relative likelihood of heat exchange process in this way or in the other way around, this is heat flow from a colder to hotter is exponentially suppressed. If you throw it out of equilibrium and check it, what happened to heat flow, this will be suppressed, is what is the Dzarzhinsky-Ozick relation. So now they took how they started with, they take two systems to begin with, classical, two systems, and they consider phase space evolution governed by a Hamiltonian, H of psi A, HA and HB. So now in that case, you have, there is an interaction which is switched on at some time 0 to tau, let us say, no restriction on it, but I take a short time, or let us say between two times, what is happening with the Hamiltonian evolution. So I take, this is the picture of time reverse trajectory, that is we have a trajectory here and it's time reversed trajectory, let us say classical. So in that case, it is assumed that the phase space evolution is time reversal symmetric. It's a classical system. We have a time reversal symmetry for each individual trajectory there. So then I will use this kind of a structure, and what is net energy change, because there is a Hamiltonian evolution, there is a delta EA, delta EB. I have two systems. A goes from time 0 to time tau, B goes from time 0 to time tau, but there is an interaction. There is an interaction Hamiltonian which governs the evolution. In such a case, the heat which is on a trajectory y, the heat is given by delta EB, because B is a hotter object, A is a colder object. This delta EB is roughly equal to minus delta EA, because energy in the process is conserved. What I am trying to say is there is no work done, only heat is there. Energy is conserved, so heat is going to be delta EB is minus delta EA is what they say. That can be seen. So in that case, they work out and derive the ratio, which turns out to be Dzarzhinsky-Ozick relation for classical phase space evolutions. So now we go ahead. If it is quantum theory, how do I do it? So there are prescriptions. This I have two systems again. both are in thermal equilibrium at temperatures TA and TB, let us say, and the system evolves under the interaction Hamiltonian, and you begin with the process of measuring energies, a projective measurement on system A and system B. So you find that EIA, EIB of the system initially, and then you allow them to interact weakly, that is weakly in the sense energy is conserved. So, and then interaction is switched off. Now you measure again the energies EFA and EFB. Let me again explain. Suppose I have a two-level system. There are two energies, E1 and E2, let us say. And then for A and B, two are there. So now if I take E1 going to E1, that is I have starting energy E1 initially, and then I go to E1 finally, that is one heat exchange. E1 minus E1, delta EA. So E1 to E2, that is 1 and 2, that is another heat exchange. There are four different finite heat quantities that can be defined in such a situation when I do a initial measurement and final measurement. And in that case, I basically have this energy conservation fine. And then what do I have? There is a heat transfer. Initial to final, it is given by EIB minus EFB. Same story like how it was done in the case of phase-space evolution, classical. They define it with the help of initial measurement and final measurement, and you find EIB minus EFB is equal to EFA minus EIA, because there is no energy is conserved, no work is done. So in such a simple situation, you do find same kind of Dzerzhinsky-Ozek relation. That is for finite dimensional system. You have Dzerzhinsky-Ozek heat exchange relation. Okay. So now our question is why it could not have been done using a phase-space trajectory, that is with Wigner phase space. Can we do it is the question first. So Wigner had formulated phase spaces. We know what is a classical phase space trajectory, and we also have a quantum Wigner phase space which is fuzzy, and probabilities are quasi probabilities. These are difficulties with quantum. But once I have a Wigner distribution function, I do have the averages are assured to me. Average quantities to be same, and suppose I have a statistical mixture, I have 2 points on phase space, but in a quantum phase space, you have a catch state and so on and so forth when I go into phase space in the Wigner sense. So this is a kind of gallery of Wigner functions, and we know that they are measured in the optics, quantum optics community. So we have methods of measuring Wigner functions, tomograms. Optical tomograms have been established. So now, how does one go ahead in order to have a Wigner function? So suppose I have a characteristic function of, let us say, for a Q operator and a P operator. I construct a characteristic function, means it is trace rho exponential this function, and that if it happens to be a Gaussian function, inverted function is also a Gaussian. So if at all I have a rho such that my characteristic function is a Gaussian function, then I have a Wigner function which is Gaussian. We choose such a thing. For example, a thermal state of a harmonic oscillator is a Gaussian, for example. If I take only harmonic oscillator state and do our Dzerzhinsky-Ozek heat exchange, what are we going to get? Because everything is kind of good and we can have a control over the situation and then see, am I able to derive such a Dzerzhinsky-Ozek relation? So now we take Hamiltonian is harmonic oscillator and I have a thermal state. Say take a temperature T. And then we know so many things. We know the Wigner function, no problem for me. So, and then the Wigner function has this kind of a form. Not that it is not simply e to the minus beta h by z of beta like in classical theory, but this has a symplectic eigenvalue, and energy U is not k into T, but it is h bar omega nu T. So now with such a thing, what we have to do is derive an analog of Jarzynski-Ozick theorem. What do we do? Take two systems. I have phase space variables psi naught, and my initial state is a product state. Each one is in temperature Ta and Tb. This is temperature Ta, this is temperature Tb. I know the Wigner function then. And then what I will do is, that is, these are all just details, but let me say that I have allowed what is a unitary interaction from beginning to final. This is the, I don't specify the unitary interaction, but I will say initially I have a HA, HB, there is an interaction, that's all. And now rho AB goes to rho AB tau, and similarly Wigner function goes to Wigner function psi at time tau. And it is simply well known because I am using a symplectic transformation. If I restrict, because my intention is to use a simplest possible case of harmonic oscillators, Gaussian Wigner function, and identify in terms of phase space distributions, how do I get Jarzynski-Ozick relation? So this is simply psi tau is related to psi of 0 through a symplectic transformation, 4 cross 4, that is fine. So the Wigner function at time tau is well known. So this is, instead of psi 0, I have a psi tau, that's all. So with that, we write now, how do I get a probability for heat in itself in this process? So basically, heat is nothing but I have a projection in the phase space delta Q minus Q naught. So in that case, when is Q is equal to Q of psi naught is what I asked, and I average over Wigner distribution function. That's what is heat evaluated. So that is my probability for heat. That's what they did in the case of classical phase space distributions too. So that is what is done here. With that, I can see that Wigner function is related to its time reversed twin in a particular way. W of psi 0 bar, that is on the reverse path, it has this factor coming in, which is seen in the derivation, same as classical theory. And then I get ratio between P of Q and P of minus Q has a factor again. But that factor is not same as that in the case of classical, that is Jarzynski-Ozick, classical as well as quantum. So we have a delta beta, what I write as omega, it's a frequency dependent factor. Delta beta does not have any frequency of a harmonic oscillator, but we get something which is frequency dependent term. And what we are talking about is Jarzynski-Ozick two-time or double projection method is this. That is, heat exchange is given by this. But what is Jarzynski-Ozick like heat exchange fluctuation relation using our Wigner function only for harmonic oscillator? That shows that there is, instead of a TB minor inverse TA inverse, you have the symplectic eigenvalues coming into picture. So how do I understand it? There is a lot of this on this that can be thought about only in the high temperature limit, or in other words, if I take H bar tending to 0 or T high temperature, I get the same thing. Yeah. So this is classical analog, fine. So there are other things that when we were thinking of this paper, we found that this Wigner function, not exactly Wigner function, but its characteristic function and a kind of series for classical limit has been identified, but not very clear expressions for heat exchange distributions are given. Sorry, work distributions were given. These are the papers, but we did it for especially what is a heat distribution, etc. This case, we can see that in the H bar tending to 0 limit, if you think of it as a classical limit, you don't have kind of uncertainty and you get exactly sharp kind of a trajectory. Then it will reduce to our Jarzynski-Ozick relation. But Jarzynski-Ozick relation holds even in the case of quantum double projection measurement. How do we deal with such a thing is the question. So now there is another thing is, people already talked about what is equipartition theorem. So we have every degree of freedom gives you a KT, that is equipartition theorem, irrespective of anything. But in the case of our quantum theory, even for a harmonic oscillator, average energy is not KT, it's going to be different. There are papers on that. We find several papers, partition of energy in a dissipative quantum. Everybody talks about oscillators and such a thing is going on. I just take 2 minutes on this. We were curious about heat exchange distribution using Wigner function, using the Dzerzhinsky-Ozek approach. These are two things that we have in mind. So if at all I take Q as my random variable and I want to know what is a moment generating function, that is exponential of some quantity times Q as a variable, take an average. Find that this is defined in terms of Wigner function again. So I do get, simplify it without going into details, we get what are Rayleigh relative entropies for Wigner function at time tau, Wigner function at time 0. So we have moment distribution function for heat exchange in terms of Rayleigh relative entropies, and this we then realize that there is another, if I take a double projection approach, I also get such Rayleigh relative entropies in terms of rho AB 0, rho AB at time tau. What am I saying here? We have two approaches. One is double projection. Do measurement initially, do the measurement finally, and look at what is the heat exchange. So that gives you a Rayleigh relative entropy generating function for heat is this kind of a function. Now, if I take a Wigner function, I get Wigner function Rayleigh relative entropy. So if I have a Gaussian function, I can compute these things, and what we have to look at is how different is this, whatever is double projection method, is from the Wigner phase space function. They are different, we know, but how different they are. So there have been some papers, that is Rayleigh relative entropy has been very recently, that is in 2022, a method of working out the Rayleigh relative entropy has been given. And also there are direct measurements of Wigner functions, not on light but on atoms, has been realized recently. So this is in optical tweezer, people have been able to measure this. There are things which have gone in that direction. And we have other things where it is a Imperial College group, Rudolph's group has shown that if you have two systems which are correlated initially, how there is a change in Dzerzhinsky-Ozek heat exchange relation. That is found to be different. If correlation go to 0, it goes to the same thing. That is, there are slight differences. Correlations result in a modification of the acceptee relation has been shown. This has been done experimentally in NMR, Mahesh's group in ISR Pune. They have shown if you plot the probability, that is what is this log of the ratio, it will be a straight line for different temperatures. But they also show that temperature, if correlations are more, if you have more correlations, heat flow in the reverse direction gets improved. That is, distribution probability gets improved. This is what has been checked, fine. But now the question is how, that is, there is also something to go. People have been talking about how measurements fill the correlations. So we should not do measurements and try to look at heat exchange, let us suppose. So how to do it? So one approach is give away, that is, let's not think about physics. Only look at what is a Bayesian network theory. Don't do any measurement, try to develop what are probabilities. So this is what was done, trajectory-based approach, but not in physics, basically. But we think that Wigner function gives you a classical quantum connection. So one should do Wigner function-based approach. So then we can actually get it. So one more recent result which I will mention. This is a heat exchange, heat distribution function as a function of exchanged heat. It's not experimental, theoretical. What is this? They have done one system is in at heat, some TA. TB is a heat bath,
and you do a Markovian evolution, and you try to do a solve the heat, that is what is heat transfer in a by solving the Lindblad equation. It is easily done for a harmonic oscillator, and they have evolved derived what is a heat exchange function theoretically, and that's what is plotted here. No two systems, one is a heat bath, one is a harmonic oscillator system. This is what is the picture. Remember that frequencies of the two, heat bath as well as the system, are same. In that case, it obeys Jarzynski-Ozick heat exchange relation. Fine. Both oscillators have same frequency. So in that case, we do find that Sudarshan had written a paper where two systems, how they relax. Don't use Markov approximate Lindblad equation, but you take two harmonic oscillators and then allow it to interact. This is a discrete kind of evolution which reaches a equilibrium. So we think that they have shown in that paper that if you take two systems, two different temperatures, relaxation depends on the frequency difference of the oscillators. I just think that harmonic oscillator we have never thought about. If the frequency is different, what happens to heat exchange? So that is what I want to highlight here. And I noticed a paper from TCG Crest here. I don't know if the author is around. This is a trimer, Gaussian trimers, and they take this is a heat, this has a heat bath, two, that is systems, three systems, and then they didn't look at what is the heat exchange distribution, but they looked at heat current. Basically what is done, they wanted to check heat current, but these are kind of inputs for us to look at what happens to trimer, harmonic oscillator, and two systems which are harmonic oscillators. And this is our paper. I thank the funding agency. And what happened? All right. I thank you for your attention. Thank you.
Any questions? Is it meaningful to study heat exchanges in this manner for closed thermodynamic cycles?
We are only looking at a simple first step where you are finding a difference between the classical and quantum. Okay, so one approach is to do a simple kind of experiment where you do initial measurement, final measurement. But if the initial and final measurements are not there, let us say, isn't it that we think that Wigner distribution function approach will be good where it is possible? If it is not possible, go beyond it. That is, if it is negative, I don't even have several things which are seen to be computable, etc. What you are asking is a cycle, Carnot cycle, or kind of a thing.
T and then back to it.
That's all. No work is not checked here. But one can check for work, one can check for entropy and all that. But the question is, if it is slightly out of equilibrium, how would the exchange follow a pattern? What is the statistics of heat exchange? That's what is explored. But it gives you different results when correlations are there. Or look at it from a phase space distribution point of view. This is something which needs to be settled, I think, in through experiments is what I think. Thank you.
Carrying on ahead with what you were discussing.
Right.
Actually, it is regarded that for Gaussian systems, whenever the Wigner function is positive,
yes,
get a classical quantum correspondence. We will not go much beyond that.
Right.
So in a way, it is surprising that even for a positive Wigner function, you are getting some frequency.
Correct.
Correct. So I wonder if you take into account correlations,
then it will be
say squeezed.
Right.
So what will be the difference?
Correct.
And then also, if you actually complete the cycle and study Carnot heat engines,
sure.
There will be lots of works in, for example, in quantum heat engines and quantum batteries.
Agreed.
So, what will be the contribution of, say, negative Wigner functions or correlations in modification? Do you have any comments?
I only think that one thing is the negative Wigner function or Even a squeezed Gaussian state is not classical. It's even if it is positive, Wigner function is positive, it won't. But still, you should have a heat exchange distribution. That is, if I can compute the Rene relative entropy there, what is double projection method, and this will be very clearly seen. I expect that the heat flow in the backward direction will improve with non-classicality. I expect that. For that, I need to do a specific example of H interaction. That will do. H interaction bringing in squeezing will do. That is a symplectic operation which causes squeezing alone. Then we will be able to do it, which we are thinking of doing. And also for entangled, that is there. But this is just a preliminary thing. Yeah. So, yeah.
Ma'am, the past law you defined, so this is valid only in delta neighborhood of equilibrium, right? This
Yes.
Rho dot and H dot.
Correct.
Heat and work. And this 2-point measurement scheme, so there the total energy exchange is considered as heat.
Correct.
Because you, but in your framework, like when you say heat distribution, so like, is it the total energy exchange or?
Okay, I had defined Q as EAI minus EAF. There are two measurements. So in a trajectory, I have an initial energy, already a property of the trajectory, energy A is given. And final, what is the energy after interaction? Difference between them is Q.
Okay.
That's
yeah, but when you are saying that, okay, we can do for work distribution also.
Yeah.
Then like how to differentiate?
Yeah, I cannot take energy conservation, that's all. That conservation is energy conservation, and heat definition is something like delta U is only delta Q, no work. That part is left out. We have to think about it. But people, it can be done. It's not that it cannot be done, but that has to be done.
No, can be done. Like it's not unique like how you define work. Not
I have a hunch that I didn't calculate, but it will still give you that beta W omega factor. Frequency dependent factor for harmonic oscillator will come. That is, if you don't take both oscillators at same frequency, you are going to find a difference in Wigner function approach. That's what I will predict.
My question was that in your Wigner function diagram, you have some non-classical behaviors. What is the reason for that, and how can we simulate, incorporate squeeze state into that?
Okay, so basically the non-classicality part is originally identified as non-commutativity. Q and P do not commute with each other. So whenever you have non-commuting observables being considered as random variables, that is phase space variables, you are supposed to get what is called as you will get quasi-probabilities. But there are different approaches, correspondence rules for classical functions to quantum operators. These correspondence rules, if you take a particular correspondence rule, you get what is called as a Q function, which is always positive, but it doesn't have similar properties for whatever. Every positive operator is not a positive function. Kind of differences are there. It's not a single conclusive statement which tells you about non-classicality. There are layers of that. Okay, squeezed states or something in that domain, I will say.
No other question? Just thank again. Oh, seriously.
Yes, thank you.
So the question, why did you think that there might be a correspondence between the Wigner distribution approach and the projective measure?
Yeah. When I read the paper by Dzarzhinsky-Ozek, they talk about a classical phase space. And when it comes to quantum, they only think about a projective measurement.
But I agree. But in quantum domain, things are different.
Agreed.
See, the projective measurement approach they have taken, I guess, because there is no observable for what?
Right.
Quantum.
Agreed.
And if you do projective measurement, it will destroy.
Right.
So
right.
One should do something which will, destroy, but very little.
Right.
So maybe one can think about like weak measurement or something like that.
Fine, fine.
So at the outset, I would say these are two different things, so they will give different results.
Right. We did try weak measurements. Not much of a difference.
Oh,
It
I
is
see.
the same. I didn't find any much of a difference between projective measurement and this, which is well within the thermodynamic theory and well within the Jarzynski-Wozik relation. No change. So if I try to construct a heat distribution function in all these cases, like how Mahesh's experiment shows different distributions. So if you do that, you will find the suppressed heat flow in the reverse direction in all the cases. But why not Wigner function is a question that we got. It can be done. At least in the case of Gaussians, it can be surely done. And formalism, no difference. Classical and quantum. But results are different. Why is the question.
The other question is, in practice, you don't. So here you are taking energy conservation.
Correct.
So what if I just go beyond energy conservation?
Right. Yeah.
So what sort of thing you can expect?
Right. That's what I told Abhijit also. So that is to take a system similar, harmonic oscillator, easily solvable, pedagogic, everything is fine. So even in that case, you are going to get a beta W factor with no energy conservation also. Because you check the entropy or the work done where there is no energy conservation. In such cases, you will find similar beta W factor. So this is only a kind of highlighting thing where there is a difference. One has to think about it. And other things have shown already if there is a correlation, there is a difference and kind of things. And not from a physics thing, but from a probability theory wise trajectory approach has also been done. There are other things which is important to know the real limit from our quantum theory on the heat exchange or whatever exchange fluctuations is what I believe. Thank you.
So let us thank the speaker again.
Dr. Prasenjit Dev has some announcement. Yeah.
Request all our participants and speakers to wait in the lobby for a few minutes. Our volunteers will assist you in reaching the lunch venue. Thank you.